Hello my dear students, welcome to my YouTube channel that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is the sp3 hybridization, but this time we are going to have two lone pairs in the main structure. In the previous lecture we have done about the sp3 hybridization with one lone pair in the structure. So today we are going to do two lone pairs in the main structure in sp3 hybridization. So let's start. So today's example for sp3 hybridization is H2O, water molecule. So today we are going to study about the hybridization in water molecule, that's H2O. Before doing that, let's make the Lewis structure for the H2O molecule. That's our oxygen, that's the hydrogen, that's the hydrogen. Now let's talk about the oxygen. What's the atomic number of oxygen? That's 8. So the configuration will be 2, 6. That means oxygen is having 6 valence electron in its valence shell. So I'm going to mark 6 electrons in the valence shell of oxygen. That's first electron, second, third, fourth, fifth, and the sixth. Now let's talk about the hydrogen. The atomic number of hydrogen is 1. So its electronic configuration is 1. That means hydrogen is having 1 electron in its valence shell. So I'm marking 1 electron with the first hydrogen and again 1 electron with the second hydrogen. Now let's make the bond between them. That's the bond of first hydrogen with oxygen. That's the bond of second hydrogen with the oxygen. Now let's count the number of valence electron in first hydrogen after the formation of one bond with oxygen. That's the first electron, that's the second electron. That means hydrogen has attained its octet, that is 2 electron in its valence shell after the formation of one bond with oxygen. Now let's talk about the second hydrogen. I'm counting the number of valence electron of second hydrogen after the formation of bond with oxygen. That's the first electron, that's the second electron. That means second hydrogen has also attained a duplet, that's of 2 electron in its valence shell after the formation of one bond with one oxygen atom. Now after that, let's count the number of valence electron in oxygen after the formation of two bonds with two hydrogen. That's the first electron, second electron, third electron, fourth electron, fifth electron, sixth electron, seventh electron, and the eighth electron. That means oxygen has also attained octet, that's 8 electron in its valence shell after the formation of two bonds with hydrogen. That means oxygen has attained the valence electronic configuration of noble gas, that's neon, that it has attained 8 electron in its valence shell. Now let's talk about the central atom in case of water molecule. Here the central atom will be obviously oxygen, because oxygen is forming two bonds, the maximum number of bonds in H2O molecule. So we are going to talk about the hybridization in oxygen atom. Now before doing that, let me mark one thing first for you. If any hybrid orbital is having two electrons with opposite spin, comma, then that pair of electron, that two electrons, or we can say pair of electrons, will be regarded as the lone pair of electrons. Will be regarded as lone pair of electrons. Now let's come back to oxygen atom. What's the atomic number of oxygen atom? It's 8. What's the valence electronic configuration of oxygen in terms of subshell? It will be 2s2 2p4. Now let's draw the orbital diagram in the form of boxes. As subshell is having only one orbital, so that will be the 2s. The 2p subshell has 3 orbitals and they are degenerate in nature. Degenerate orbitals are those whose energies are equal. So that's 2px, 2py and 2pz, and the combination of these 3 orbitals will be called as 2p subshell. Now let's fill the electrons. The 2s is having 2 electrons, so that's the first electron and that's the second electron. Now 2p is having 4 electrons, so while filling the 4 electrons we have to follow the Hund's rule, and it states that firstly all the degenerate orbitals. Here degenerate orbitals are 2px, 2py and 2pz as their energies are equal. So in case of degenerate orbitals, while filling the electron, firstly all the orbitals will get 1 electron each. After that pairing will start, and this rule is for degenerate orbitals. Here energy of 2px, 2py and 2pz is equal. So let's fill the 4 electron. So that's the first electron, second electron, third electron, and that's our fourth electron. And this is the ground state of the oxygen. Now let's come back to the Lewis structure. In the Lewis structure, oxygen is forming 2 bonds. That means in case of oxygen, there must be 2 orbitals containing 1 electron each, so that 2 orbitals of oxygen having 1 electron can overlap with the atomic orbitals of hydrogen, that's 1s of hydrogen, to make the 2 sigma bonds. So that means we need to have in the Lewis structure, let's come firstly to the Lewis structure. In the Lewis structure, oxygen is forming 2 bonds and both the bonds are sigma bonds. So oxygen is forming 2 sigma bonds. So accordingly that oxygen must have 2 atomic orbitals containing 1 electron each, so that oxygen will become eligible to overlap with the 1s orbital of 2 hydrogens containing 1 electron to form the sigma bond. So let's come back to the orbital diagram of oxygen. In case of 2py and 2pz, here you can observe that the 2py and the 2pz is having 1 electron each. So now oxygen is eligible to form the 2 sigma bonds with the 2 hydrogen atoms. Now from here we don't need to excite any electron, so ground state will be sufficient. So hybridization will take place in the ground state only. And what is hybridization? It's the intermixing of atomic orbitals. Now there is always intermixing of all the atomic orbitals containing electrons in the valence shell. What is the valence shell? The combination of 2s and 2p. The 2s subshell plus 2p subshell will make the valence shell, and we have to mix all the orbitals which are having electrons. So that means 2s is having electrons, 2px is having electron, 2py and 2pz all are having electrons. So the orbital of only valence shell will intermix to form the new hybrid orbitals. So here that means 1s and 3p orbitals will intermix. And one rule I have told you in the previous lecture also, that in case of hybridization, the orbital of s subshell, or we can say s orbital, will always be involved. There is not any hybridization which is not having the s orbitals. So here in this case 1s and 3p orbitals will intermix, and this intermixing of atomic orbitals is called hybridization. So here total of 4 atomic orbitals are mixing, 1s and 3p. They are total 4 in number. So we are going to have 4 new hybrid orbitals. And one very important thing, that 4 hybrid orbitals will be degenerate in nature. That means the energies of 4 hybrid orbitals will be equal. So we have mixed the 4 atomic orbitals, 1s and 3p, and we are going to have 4 new hybrid and degenerate orbitals. So we got the 4 new hybrid orbitals which are having equal energies. Now what type of hybridization is this? Here the 1s and 3p, 1s and 3p are intermixing. So we are going to have the hybrid orbital in which we will be having 25% S character and 75% P character. Per hybrid orbital. So the name of our hybrid orbitals will be sp3, which signifies that hybrid orbital is having 25% s character and 75% p character. As in as during the intermixing we were having the ratio of 1:3, the 1s and the 3p. So the second hybrid orbital will also again called sp3 hybrid orbital. The third orbital will be again sp3 hybrid orbital, and the fourth one will again sp3 hybrid orbitals. So by mixing 1s and 3p orbitals of oxygen, we are going to have 4 new hybrid orbitals, and each hybrid orbital will be named as sp3 hybrid orbital, as it is having 25% S character and the 75% P character. So we got the 4 new hybrid orbitals, that's sp3 hybrid orbitals. Now let's come to the electrons. How many electrons were there in the second shell or in the 2s and the 2p subshell in total? We were having 2 electrons in the 2s and 4 electrons in the 2p. So we were having total of 6 electrons. The 2 electrons are present in 2s and the 4 electrons are present in 2p. So in total we were having the 6 electrons, and now we have to fill the 6 electrons in the hybrid orbitals according to the Hund's rule. That is, firstly all the hybrid orbitals will get 1 electron each. After that the pairing will start. So we are going to fill the 6 electrons. That's the first electron, second electron, third electron, fourth electron, fifth electron, and the sixth electron. So we got total of 6 electrons in 4 sp3 hybrid orbitals. Now let's come to the initial points. Here I have already told you, if any hybrid orbital is having 2 electrons with the opposite spin, then that 2 electrons or pair of electrons will be regarded as the lone pair of electrons. So that means in this case we are having first 2 sp3 hybrid orbitals which are having 2 electrons each, that is this one and this one. So this will be called as the lone pair of electrons, and another is also lone pair of electrons. Now let's talk about the hydrogen. What's the atomic number of hydrogen? That's 1. So what will be the orbital configuration of hydrogen? It will be 1s1. So that means in total we are having 2 hydrogen. Now the 1s subshell is having only 1 orbital. That's the 1s of first hydrogen atom, which is having 1 electron. So now this 1s of hydrogen will have the head-on overlap with the sp3 hybrid orbital of oxygen to form the sigma bond. So we got the sigma bond that has been formed between sp3 hybrid orbital of the oxygen and the s orbital of the hydrogen by head-on overlapping. Now we were having total of two hydrogens. So let's make the second hydrogen. In second hydrogen also, we are going to have one orbital in s subshell whose configuration will be 1s1, that's for hydrogen, as having one electron. Now here again, this 1s orbital of hydrogen will have an head-on overlap with the sp3 hybrid orbital of the oxygen to form the sigma bond. So we got the sigma bond that has been formed between sp3 hybrid orbital of oxygen and the s orbital of hydrogen by the head-on overlap. So we got the exact hybridization of the oxygen in case of H2O molecule. Now let's come to the structure. Now I'm talking about the structure. Here which type of hybridization we got? That's sp3. In sp3 hybridization, what is the standard geometry we are having? That's called tetrahedral geometry. Now let's make the structure. We are having oxygen over here. Now oxygen is having two lone pairs. The first lone pair in first sp3 hybrid orbital, second lone pair in second sp3 hybrid orbital. So we are going to make that lone pairs. So that's the first lone pair. That's the second lone pair. Now oxygen has formed two sigma bonds with two hydrogen. So that's the first hydrogen, and the sigma bond formed will be sigma sp3s, because this sigma bond has been formed by head-on overlap of sp3 hybrid orbital of oxygen with the s orbital of hydrogen. Now let's make the second sigma bond with the second hydrogen. Here also this sigma bond is again sp3s, which has been formed by head-on overlap of sp3 hybrid orbital of oxygen atom with the s orbital of hydrogen atom. So as both the sigma bonds are of same type, that is sigma sp3s, so the bond energies or the bond strength of both these sigma bonds will be equal. Now let's talk about the bond angle. The bond angle in case of water molecule is 104 degrees. Now the normal tetrahedral angle is 109 degrees and 28 minutes. Now the bond angle has decreased to 104 degree. It's the reason we will be doing in the Vesper theory, that's valence shell electron pair repulsion theory. I'm repeating, the valence shell electron pair repulsion theory will answer this question, that why this bond angle is decreasing from the standard tetrahedral angle of 109 degrees and 28 minutes. Now let's come to the very important point. Here the normal or the standard sp3 geometry is tetrahedral, but in this case we got the two lone pairs. So while naming the geometry, we don't consider the lone pairs. So this geometry will be called as V shape, or another name is bent geometry, and it will not be named as tetrahedral now because it is having two lone pairs. So while naming the geometry, we don't consider the lone pairs, so we are left with just V shape, or we can say the bent shape in case of H2O molecule if sp3 hybridization is having two lone pairs. We don't consider the lone pair while naming the geometry, so here the name of H2O structure will be V shape or the bent. Now at last let's come to the energy points. Here is one endothermic process, and that's the intermixing of 1s and 3p orbitals. So that's called hybridization energy. So during the mixing of 1s and 3p, there will be consumption. There will be consumption of energy called hybridization energy. So that's our first endothermic process, that is the energy is absorbed and which is called as hybridization energy. So that's why I have written the consumption of hybridization energy, that is during the intermixing of 1s and 3p orbital the energy is consumed, which is called the hybridization energy. Now during the formation of two new sigma bonds, here I am writing during the formation of two new sigma bonds between oxygen and hydrogen, comma, there is release of energy. There is release of energy, or in chemistry you can say that whenever there is a bond formation, that's an exothermic process. So here during the formation of two sigma bonds there is a release of energy. It's an exothermic process which compensates or recovers, which compensates or we can say recover the hybridization energy. Due to which the formation of H2O molecule is feasible or possible. So in any process, whenever there is an absorption of energy, at the end that absorbed energy must be recovered. In this case, hybridization energy was consumed. So at the end, that hybridization energy is compensated by the energy released during the formation of two new sigma bonds, that sigma sp3s, between the oxygen and the hydrogen. So due to the compensation of the hybridization energy, the formation of H2O molecule is practically feasible. So I hope you all understood today's lecture of sp3 hybridization with two lone pairs in the structure. So that's all for today. I hope you all understood today's lecture. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.